This screencast is going to continue the introduction to bonding and in particular nomenclature, or how we name things. Okay, in order to determine how to name a compound, we're actually going to have to determine the type of bonding involved. And we're going to need to know how to classify elements as metals, nonmetals, metalloids on the periodic table in order to determine that. Once we determine the type of bond, then we can determine the type of name to use. Right? We're going to compare ionic and covalent, but we're going to focus on ionic bonding in detail. Covalent will be in a future screencast. We're also going to define a term, electronegativity, and kind of see how that affects the bond character, whether that bond is ionic or covalent. So the first step is looking at the periodic table and determining whether the element is a metal or a nonmetal, or whether it's a metalloid. And you can see from this periodic table that most of the elements on the periodic table are metals. You might want to make some notes on your own periodic table that was given to you in class, that paper, your very best friend. Right. So, like I said, most of the elements on the periodic table are metals. Okay. When we talk about covalent bonding, at least in the beginning, we're going to focus really on main group elements. All right, and those are these metals that are in these two groups. We will talk about some of the metals in this area a little later. And then hopefully you can see that on the right side, the upper right, these are your nonmetals. Hydrogen is included as a nonmetal. It's put in this group on the periodic table because it has that one valence electron. Okay. So remember, group 1, 1 valence electron, group 2, 2 valence electrons, 3, 4, 5, 6, 7, and 8. If you notice, metals all have a smaller number of valence electrons. The nonmetals have more valence electrons. So types of bonds. We are going to look at 3 types of bonds, and that is ionic bonds, covalent bonds, and metallic bonds. I struggle with my pen a little bit. All right, so ionic bonds. These are the ones we're going to focus on first, and then we'll look at covalent. But ionic bonds form between metals and nonmetals. Okay, that's why it's important that we can identify an element from the periodic table as being a metal or a non-metal, so that we can tell if 2 of those are together, more than likely it's an ionic bond. The structure of a bond that forms between a metal and a nonmetal forms what's called a crystalline structure, and it's this whole big structure, and we'll talk a little bit more about what this really represents in just a little bit. Covalent bonds form between 2 or more nonmetals. These form what we call molecules. H2O is typically what everybody thinks of when they talk about bonding and how things form. All right, so it's a like standalone unit is a molecule. This involves sharing of electrons. And ionic bonds is actually a transfer of electrons. And I did want to show a bunch of molecules together to kind of reference the differences between these 2 structures. All right, and then we will talk briefly about metallic bonds. These this should be form. These form between metal atoms. All right, what happens is the valence electrons or metals are held rather loosely, okay, and they actually are able to kind of flow through the metals, the inner part of the metal. Okay, we call them metal ions. It's the atom with the valence electrons being able to flow. I hope that makes some sense. Okay, so using those terms, hang on. Let's use the placements of the elements and whether they are metal, non-metal, or metalloid to define or classify these four compounds as either being ionic, covalent, or metallic. So looking at this, we can see, hopefully you can identify that there's two elements involved. Barium is here. Hopefully you would identify that as being a metal. Chlorine is over here. Hopefully you would identify that as being a nonmetal. You do need to memorize that a bond between a metal and a nonmetal is going to be ionic, so this would be ionic. Looking at the next one. Again, I hope that you can identify that these are two elements. I do have more than one chlorine atom, but they are just two elements bonded together. Carbon here. Maybe I should change my pen color. Change it to green. Carbon is here. And then chlorine again is here. Carbon, hopefully you can identify as being a nonmetal because it is on the upper right, and it is on the upper right over the metalloid break. Two nonmetals, you should identify this as being covalent. Fe, I only have one element, and where is it located? Here. It is a metal, so this would form a metallic bond. And then the last one, I have copper, and then I have this. This is something that we're going to look at later. This is what is called a polyatomic ion. This happens to be the sulfate ion, which is an SO4 - 2. It's called an ion. So what kind of bond do you think is involved? Hopefully you guessed correctly, ionic. All right? So an ionic bond will have these polyatomics in them. For the most part, it is going to be a metal plus a polyatomic. All right, so for the most part, it is a metal plus a polyatomic. There is one exception, and that's things with the polyatomic ammonium, and that because it's the positive would bond with a nonmetal. And let's take a look at that. Okay, so we're going to see what the okay, so review. Why do atoms bond? Atoms bond to become stable. I guess I should say to become stable. And how do they do that? They lose, gain, or share electrons to achieve, did I spell that right? Achieve 8 electrons in the outermost energy level. Okay, so what is this ionic bond? An ionic bond is an electrostatic force that holds ions together in an ionic compound. Electrostatic force really just means it can either be an attractive or a repulsive force between charged, I'm going to say particles. That's an A, particles. Okay, so in an ionic bond, it's going to be an attractive force between cations and anions. And I guess I should say between. So how do ionic bonds? Well, from our earlier discussion, we form how do ionic bonds form? Well, remember ionic bonds form between metals and nonmetals. And what we see is an electron's transfer from the metal to the nonmetal. So metals form the cations because they're going to lose electrons. Nonmetals form the anions because they're going to gain the electrons. Then there's that attractive force between these cations and these anions. So how do I know when atoms will gain, lose, or share electrons to satisfy that octet rule? It has to do with something called electronegativity. Electronegativity is a measure, okay, of the ability of an atom to attract a pair of electrons in a chemical bond. So it's really almost like a tug of war between two atoms. Okay, so we can think of it as a tug of war. For a pair of electrons. If one atom has a much higher electronegativity, it has the ability to attract an electron, or a pair of electrons technically, to itself much more than the other atom. If two atoms are about the same electronegativity, neither one of them is strong enough to pull the electron away from the other, and they end up sharing. So how do we know what elements are higher or lower in electronegativity? Okay. Turns out, if we look at, let's look at lithium, 0.98. Let's look at fluorine, 3.98, right? So nonmetals tend to be high electronegativities. That says electronegativities. Metals tend to have low electronegativities. That's a long word. Okay, so what this means is that nonmetals, when they meet up with a metal, are able to steal or to attract the valence electrons of those metals to themselves. So metals have low, they tend to lose electrons because they don't have the ability to keep them attracted to themselves. They form cations. Nonmetals, high electronegativities, they tend to gain electrons, they tend to form those anions. Okay. So for example, let's look at sodium chloride. Sodium is an element, chlorine is an element. Remember, that is a diatomic in your Hofbrinkel. And yes, you still have to remember Hofbrinkel. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine all form diatomic elements. Okay. Anyway, so sodium is a metal, Chlorine is a nonmetal. Make sure that you can identify that looking at your periodic table from where they're located. Sodium, 1 valence electron. Okay. In the bonding process, these chlorines are going to split apart to form just an atom of chlorine. Okay. May not be exactly quite right, but we can look at it that way. Okay, so chlorine in group 7 has 7 valence electrons. Higher electronegativity, sodium has a pretty low electronegativity. Chlorine is able to attract that electron over to itself, basically winning the tug of war for that pair of electrons now. Okay. Sodium is left being a cation, chlorine is left being an anion. These positively charged ion is attracted to the negatively charged ion to form sodium chloride. What does that look like? It looks like this. This is what sodium chloride would look like. Sodium is going to be the red spheres, and those would be sodium ions. Chlorine is going to be the yellow spheres, and that's going to be the negatively charged ion of chlorine. Keep in mind, this is negatively charged. It is going to be attractive to a cation on all sides. Okay, so its closest neighbors are going to be sodium ions in all directions. And you can say the same thing for a sodium ion. It's going to be attractive on all sides to the anion. So it's surrounded. It forms this whole big structure. So I don't have just one sodium and one chloride. I have many, many sodiums surrounded by many, many chlorides. And I get this crystalline structure. Also sometimes called a lattice structure, because it kind of looks like a lattice fence with the cations and anions in the crosses of that lattice fence. Okay, so let's talk briefly about comparison of ionic and covalent compounds. An ionic bond is made up of a metal and a nonmetal. There is a large difference in the electronegativity. Electrons are transferred from the metal because of the low electronegativity, not as much of an attractive force keeping its valence electrons in the atom. Those electrons from the metal transfer to the nonmetal that has the higher electronegativity, can attract electrons to itself, forms anions. You can think of this as a little brother, big brother. I should say a big mean brother who might steal candy from his little brother. Covalent, two nonmetals, small difference in electronegativity. Neither one of those nonmetals can pull electrons, can steal an electron from another nonmetal, so the electrons end up being shared. Be like twins, kind of equal strength. They're exactly the same. Neither one of them has a high enough electronegativity to take the electron away from the other. Keep in mind, the important thing here too is that the bond type is going to dictate physical and chemical properties of compounds. Because in this ionic structure, we are making a crystalline, that crystalline structure, that's going to have very different properties from a covalent, which makes molecules. So, how do we determine what ions elements are going to typically form when we're talking about ionic compounds? Well, earlier we had talked about valence electrons, groups 1, 2, 3, 4, 5, 6, 7, and 8. We talked about sodium having that one electron. To complete the octet, sodium really has two choices. It can lose this one electron, or it can gain 7. What is easier to do? it's easier to lose that one electron. All of the elements, with the exception of hydrogen, in group 1 tend to form +1 ions. Group 2, something like magnesium, has 2 valence electrons. To satisfy the octet rule, it could either lose these 2 or gain 6. Easier to lose 2. Losing 2 electrons makes it a +2 ion. Elements in group 2 tend to form +2 ions. Boron is kind of a weird element, so we're going to kind of forget about this. But aluminum, okay, 3 valence electrons tends to form a +3 ion. I'm going to jump over here to fluorine. Fluorine has 7 valence electrons. It could either gain 1 to complete the octet or lose 7. Hopefully you're going to agree that it's easier to gain 1. Elements in group 7 tend to form -1 ions. Similarly, group 6 with its 6 valence electrons forms -2 ions. Group 5 valence electrons, usually gains 3 electrons to complete the octet to form a -3 ion. These elements typically share. Remember, these elements in that 8th group are already stable. They don't tend to react. Because they are already stable, they don't need to react to gain stability. So there you see pretty much what we just saw. There are 2 elements that you do need to memorize what their stable ions will be. That is zinc. You need to memorize that zinc always forms a +2 ion. You also need to memorize that silver always forms a +1 ion. Okay. Green areas we'll talk about shortly in another screencast. They tend to form ions with more than 1 charge. White areas don't usually form ions, they tend to share. Okay, so using our newfound knowledge, let's predict what ion forms. So if we're looking at magnesium, magnesium is right here. It's in group 2. They tend to form +2 ions. So I would write magnesium as a 2+ with its ion. Phosphorus is here. It is in group 5. It has 5 valence electrons. 1, 2, 3, 4, 5. That kind of ends up with a curly Q. It is going to gain 3 electrons rather than lose those 5, so it would form a -3 ion, and we would write that as a P3-. Chlorine here in group 7 or 17, 7 valence electrons, is going to form a -1, and we would write that ion that way. Argon is over here. That's in group 8 or 18. It doesn't form an ion. Put that in there as a trick. Because it's already stable with its 8 valence electrons. And that's the end of the screencast.